Hello, everyone. My name is Michele Campbell, and my project was multi-scale modeling of the effect of high magnetic fields on steel alloy treatment. I came to UF from the University of California, Merced, where I double majored in material science and engineering and computer science and engineering. Upon my graduation in December, I plan on applying to various materials PhD programs. During my time in the CERT program under the Herbert Wertham College of Engineering, my project was part of a collaboration between the lab groups of Dr. Hennig and Dr. Tonks. First, I will be introducing the larger overall project my experience contributed to. The induction coupled thermomagnetic processing project combines inductive heating with magnetic fields to treat materials. The Tonks and Hennig groups are developing computational methods to simulate the behavior of steels for commercial implementation. This project came about because heat treatment of steel is energy intensive. Most energies are wasted as heat due to older industrial systems. By modifying the treatment and post-processing steps, energy can be saved and the materials properties of the steels can be refined. Overall, the project aims to demonstrate industry-relevant ITMP at a large scale. Due to its size, this project features many collaborations from other institutions and companies shown here. Now transitioning to my portion, in order to advance the ITMP project and fulfill the goals of energy-efficient heat-treated steels on a commercial scale, I first became familiar with atomic scale methods such as density functional theory and UF3 machine learning potentials. With these as the foundation, I contributed to the Monte Carlo simulations on the BCC and FCC iron carbon system. The free energies found from the atomic scale serve as the bridging data from the atomic scale to the mesoscale. From there, I developed a phase field model that represented the behavior of steels in a magnetic field. Starting off at the atomic scale, the Monte Carlo simulations were the primary focus of my summer. As we want to calculate the free energies of the system, quick and accurate energy evaluation from the Monte Carlo steps are preferred. The standard method, DFT, is highly accurate but slow. Previously, Dr. Hennig's group had generated an iron carbon data set that contained information on the BCC and FCC systems, namely the energies and forces. This data set has been used to train and validate the machine learning model. In Hennig's group's case, the machine learning model UF shown in this figure in the bottom left is significant due to its low computational cost and low normalized error. The UF3 model, which stands for ultra-fast force fields, takes the DFT dataset and calculates the internal energy of the ensemble at 0 degrees Kelvin, along with the forces on all of the atoms based on the 2 and 3 body interactions. As shown in these figures, the DFT and UF3 predicted values are comparable with low root mean squared error. My contribution was in the integration and implementation of the UF3 model within the Monte Carlo simulations, which should be able to calculate the free energies. I used Python to develop a program that utilized the trained UF3 model to calculate the energies of each ensemble. The energies were compared within the Metropolis algorithm to find equilibrium conditions. These conditions can be used to derive an expression of free energies in terms of carbon concentration, temperature, and magnetic field. In the mesoscale, I used the multi-physics object-oriented simulation environment, or MOOS, to develop an iron carbon phase field model that represents the BCC ferrite and FCC austenite phases. The free energies from the atomic scale Monte Carlo simulations are used as an input into this model. Unfortunately, due to time constraints, the model I made instead will be able to verify the free energies received from the atomic scale calculations. In this figure, I have plotted the ferrite fractions from various carbon concentration MOOS simulations, which are shown to be comparable to the expected ferrite fractions one would see in a real-life steel as calculated from the lever rule shown here. This proves that the model is working as intended and will be ready to accept the free energy expression once it is derived. Since I plan on remaining affiliated with my research groups here, some future work would include testing the Monte Carlo code based off other results found in literature to ensure it works properly, verifying the robustness of the existing DFT dataset in order to produce a well-trained model, generating the expression of free energies, and finally, inputting this function into the MOOS model to model the behavior of the steel in various conditions. I would like to acknowledge and thank SURF and the Herbert Wertham College of Engineering for sponsoring this experience and funding my summer. I would also like to thank my PIs and my mentors, Ming and Chris, for mentoring me and teaching me and allowing me to complete my project throughout the summer. Thank you everyone for listening.